Morphodynamics.
It's coming.
And I'm here from the ISIS department in Austin, Texas. I'm working with a computational hydraulics group, and these are some of my collaborators, maybe notably, Clint Dawson and Jonas Westering here. All right. So here's an overview of the talk. So first I want to provide a little bit of motivation as to why our group's interested in this topic and where we're going with it, our application models and our application motivations. Then I want to get a little bit into the governing equations and get my fingers a little bit dirty with the math, which I apologize for. Maybe not quite as dirty as the last talk, unfortunately, because that was very nice. But and then I want to talk a little bit more about how we are going to code up these equations, and then finally I'm going to show a couple of examples. I don't know if I'm going to get to this second example, which is the p-enrichment schemes. I think I planned a little bit too much, so let me just say a little something as a preface. In DG methods you have HP adaptivity, and so is generally the way people talk about it, which is just AMR with, so basically you have a local spectral method, and then you can do mesh adaptation on top of that, and there's some sort of balancing and switching between them that you can do. And so, but the thing is with DG, if you choose the right basis and you have some sort of hierarchical basis, it's very easy to do p-enrichment. We call it p-enrichment instead of p-adaptivity because the goal, of course, is to take a polynomial degree, which is strongly correlated to the order of the method, and to get some sort of some sort of real number in between two integer degrees. So say you're at degree 1 and degree 2, you want to p-enrich elements so that you can hit somewhere in between, like p 1.2. And if you can do that, if you can enrich your solution so that you're at a higher order than just a fixed integer order, then you've succeeded. And that's all you care about, right? Of course, that's not a validation study. That's entirely driven by a verification type of idea, but that's the way that we've sort of approached it. So it's something to consider. There's a lot of people here thinking about AMR, but you might want to consider doing some p-enrichment, just because it's quite easy, actually. All right. So we look at these rather large meshes of Gulf of Mexico. Here we have the southern coast of Mississippi and Louisiana here. This is the Mississippi River Delta. And we have, these meshes usually have about 10 million elements. The scales are quite dramatic, from about 20 kilometers to all the way down to 10 to 20 meters. This is the actual mesh. This is the actual mesh as well. This is not a satellite image. So we get quite a bit. These are fixed meshes, though. We don't do a lot of AMR on this particular model. And what we've used these for is mostly hurricane storm surge. So we use these, when hurricanes like Ike and stuff come in, we want to be able to predict how much storm surge there's going to be along these coasts. So we know, for example, whether we want to evacuate New Orleans before a catastrophic event comes in. And so that's sort of where we're looking with this. And we've had actually a lot of success with validation studies in terms of being able to predict that quite well with our DG method, as well as the CG code, which is related as well. And so the question is, where can we go from here? So that's where we're coming from. So what we're looking at right now is what we have added is a morphodynamic model to this traditionally shallow water equation. So what is morphodynamics? So morphodynamics is basically the question of how is sediment morphology driven by the hydraulics or the hydrodynamic equations, so that you get sediment movement along these things. So if you look at this, you see there's a lot of structure in this inland sort of watershed area. A lot of these rivers, we have all of this structure in our mesh. So we don't just have the ocean structure, we have a lot of additional structure here that we can use. So the question is, what is the sort of characteristic of these morphodynamic things? And it turns out that there's a lot of recurring multiscale, recurring features that you see when you look at morphodynamic structures. So for example, if you look here at the head of pass, this Mississippi River Delta, Bird's Foot Delta here, you see these dendritic structures, they're called in geosciences sometimes. And so what that is just these sort of tree structures here that you see coming out. Now this is a much larger scale here. This is Russia's Pudorana Plateau, and this is driven by volcanic flows. So this is over, hundreds of years here. And so, but then this here is at a much more micro scale here, and you see a similar type of feature and just in sand on a beach. And so these are the types of structures that just keep recurring. And so the question is, how can we sort of recover those types of features just by using a shallow water equation? And so the major features that we want to be able to get are sand ridges that you see in, near coast, mudslides, debris flows, avalanches, flow slides, Sturtstrom, which is an exotic and really interesting type of driven flow, sediment flow, sleeches, Zoologic, and so forth.
What's a Sturtstrom?
Sorry?
Sturtstrom?
Yeah, Sturtstrom. I don't know the etymology. Basically, what it is it's a little bit of a mysterious type of flow that is when the horizontal movement of the sediment is dramatically larger than the vertical drop. So you get, say, 30, 40 meters of horizontal movement, foot, or a tenth of a meter vertical drop. And so it's caused by internal resonances in the granules and stuff. It's not particularly well understood, but it's very exotic, very interesting, and it can lead to very catastrophic things like mudslides and stuff like this. Okay, so why are we interested? So we're interested because this stuff happens, particularly during storm surge, hurricanes and so forth. We see coastal erosion and things like this where people's homes actually fall into the sea. You lose parts of highways. You get this, bridge scour. A lot of damage can be caused, particularly during hurricanes. And so our question is, if we can fairly well predict the storm surge that's going to occur along coastlines, can we also predict these types of features that might occur along coastal regions that have sediment laws that we can put in? So, so what kind of governing equations are we looking at? So this seems like a big problem, right? So, so we take the standard extension of the one-dimensional shallow water equations to the two-dimensional form, which some people call the standard two-dimensional shallow water equations, which is just this first equation here, which is the conservation of mass. This is conservation of momentum. These two equations together is just the standard barotropic Navier-Stokes equation, except for that you have this additional so-called non-conservative product. So in some of the mathy circles that I run in, this guy creates an enormous amount of basically a mill for papers. So this is a very upsetting feature of the situation because it can't be put into a divergence form, and it leads to certain things like non-uniqueness. This is a mathematical, maybe a pedantic issue that we don't need to think about, but it is kind of an interesting thing to at least bear in mind. Now the third equation here is the Exner equation, and this equation is from the geosciences. Exner was an Austrian, I think, at the turn of the 20th century, was writing stuff. So this formalism has been around for a really long time and has been thoroughly studied. I mean, just thousands and thousands of papers on this stuff. And the form here is just really, as you can see, just an advection diffusion type equation. But this guy right here is going to end up playing a role. And now we've indexed these by I, so we're using a stratification. So we have L layers of sediment. So we have layers stacked on top of other layers, and so we can deal with something like that. I should just, for those of you maybe not familiar, H is the water column height, the total water column height. B is the bathymetry, so that's just the bed, the ocean floor, the sediment floor of the ocean. Zeta here is the free surface height. So if you have a geode, you have the bathymetry. So, well, and then the total water column height, and then the free surface. Okay. Q tilde is going to be the sediment discharge flux, and that's going to be the thrust of a lot of what's going on here. So as you can see, so what I like to say here is that this equation is often called the sediment, the Exner equation in geosciences, but mathematically this is not really an equation. This is a family of equations because sure they're indexed by I, but Q's are in fact also indexed by types of sediment, types of stratigraphic granulometry. Basically the degree of the slope of the bathymetry. So all of this will affect what the actual form of Q is. And so you have this what I like to think of as a functor here. So you actually have a functor that takes the category of solutions to the category of sediment fluxes here. So this is a family of equations that is really quite difficult, because if you're going to think about it in terms of numerical analysis, you have to think about it in terms of this. You have to be able to deal with a lot of sort of things that you're dealing with. And I'm talking about later about how to think about this. All right, so the first thing we're going to do is we're just going to drop the diffusion part and look at the hyperbolic subsystem to make things more simple, okay? So, and this guy again, so everything is going to come down to this sediment discharge formula. And this thing is going to be, this Q tilde is going to depend on any of the functions in the state vector, okay? So it's pretty complicated. It's going to be highly nonlinear. And we're going to say we want Q tilde to have algebraic well-posedness, and I'll explain what that means here in a minute to us. So here we get a flux matrix, and this is just the normal flux matrix that you see with the shallow water equations, but now you've got these two Q tildes here that look pretty benign. It turns out they're not as benign as they appear, because these things usually are written in terms of moduluses of these zero crossing functions. And so the problem here is that this thing doesn't have a derivative. And this is actually considered physical by the community that studies this, right? Because you have, well, the derivative of this is a signum function, which is not defined at 0. And you say, okay, well, maybe the velocity doesn't cross 0. Well, the velocity crosses 0 all the time in these models, right? Because you have tides, for example. Tide goes in, tide comes out. It's crossing 0 every time it hits that period. So this thing is constantly passing through infinity, right? And you've got problems here. And this is just the tip of the iceberg, because there's so many different forms of these, and all of them, for the most part, are non-differentiable. Okay, so for example, one popular form is the grass equation. So again, like I said before, the form of this depends on what type of sediment you're looking at, what the grade of the sediment, the maximum grade, or the range of the grade of the sediment can be, what type of forcings are involved. And so here's another one. This one also is non-differentiable. This one is worse. This one is zeroth order non-differentiable, as you start getting delta functions in there. There are alternative methods, non-Exner equation types of approaches to this. I mean, this isn't a terrible thing. So I should say before, because sometimes I think I paint these as sort of, they're mathematically problematic, but I think they're empirically very precise. I mean, these are models that have been thoroughly tested and match a lot of really good data. So they're very useful. It's just that they're difficult to deal with mathematically. Yeah. So well, these are they're empirical. They're derived in a sort of engineering sense, right? You can derive them from first principles. I don't know what the equation ordering is in terms of where they come from the physics. But yeah, they can be derived from first principles in that sense. Force balancing and stuff like that. Yeah. So there are alternatives. One is this Sandridge evolution model that Juan Restrepo came up with, which is he's a physicist, and his idea here is to use these asymptotic expansions. And he does this sort of this conservation of slope, which is, his idea is really beautiful, and it's actually really nice because it ends up being a much more sort of mathematically well-posed approach. Problem is, it's extremely expensive. This would be the second order, so you need the same number of auxiliary equations for the order you want to go to. So if you want to go to fourth order, you need 4 auxiliary equations. It's too expensive to very seriously consider. And you also have to start to introduce shortwave dispersion type things, because that's going to be what drives all of the sediment in this particular example model here. Whereas in these models up here, some of the periodic structure can emerge, I think, from the sediment discharge equation itself. Okay, so here's the Jacobians for these things. So again, these look pretty benign, but then and we can solve the characteristic equation, get the eigenvalues back. They're fine, but then we start to get this crazy thing when we look at the eigenvector matrix if we want to solve the Riemann problem using strong coupling, and so. And we want a strong coupling here because if we do something like localized Friedrichs or something, we end up getting a lot of instability. It turns out the strong coupling is really going to stabilize us a lot, maybe somewhat surprisingly. It's not super surprising because the sediment discharge equation is so nonlinear. And so if you don't do a strong coupling, you end up getting weird perturbations that just kill you. So you get this thing, you get the inverse of it, and then here so you might notice all these new variables and wondering, okay, well, what's alpha? What's all this? Well, look at this. I mean, this is terrible. So D, E, F. So here's right. So that's what we're dealing with, right? But we only have to do it once because once we have it, we're done, and now we can we can deal with any form for any type of sediment discharge as long as it satisfies an external equation. So that's what we did. We coded that up. Of course, in order to do all of this, we had to assume that the Jacobian existed, that we had a differentiable expression. And so we might require linearization of our representation to do that, or a multiplication or something. But it can be done. So, and then let me just say, so this is, I put this slide in here for David. This is a poor man's version of automatic differentiation. So here, all we do is, so we only have to do this once, so we don't have to worry about any optimization issues. And so the reason, and so we just throw in a character string here, whatever the form is of the sediment discharge equation, and then we can just do the symbolic differentiation here, right? And then we just, yeah, that's right. Well, I actually parse it in SymPy, but yeah, well, whatever. And then, so I parse this in SymPy, then get the Jacobian, put it out in a file, and then bring it back in and tokenize it and turn it back into bytecode, right? Slow, right? Only have to do it once. Yeah. So it's trivial. It's not. And so that's great. So now we can handle any form of this thing. Well, so okay. So let me show you some examples of this. So, all right. So here's an example of a zero crossing function. So here's a Gaussian multiplied by hyperbolic tangent, which is essentially the smooth version of a signum function, right? So look at this thing. This thing's terrible, right? This is the velocity field. It's smooth, it's differentiable at every point, it's analytic, it's trouble. So we assume that, okay, well, we've got a smooth analytic representation, we're going to get our convergence rates right? Well, no. And the reason is because of the Mercer-Roberts. I mean, the reason is because if you do a Taylor series expansion of this thing, you find out that over the domain you're looking at, this thing doesn't actually, the radius of convergence actually vanishes, right? And so, and this is something that's important to keep in mind, right? Especially, I mean, even if you're on a big mesh, if you're close to a coast, you need a radius of convergence that's going to actually be reasonable. And so if you have this what's referred to as the oscillatory structure of the function, even if it's analytic, right, you're still going to have serious problems and not expect convergence. And so that's something to bear in mind, especially I think that's something that people who are interested in H-adaptivity and AMR might bear in mind when they're doing convergence studies, which are a pain, and I've done a lot of them. And it's good to bear this in mind. All right, so, and then the non-conservative product is just this ghost in the background that is a problem. All right, so here's an example of a manufactured solution. So this is just the sediment discharge, the fully coupled shallow water sediment discharge equation. I assume this, and these are the source terms I get out. So as you can see, and this is about the simplest thing I could think of. So it gets kind of messy pretty fast. But just to show you here, Mercer-Roberts plot, if I did it out, told me that I should have started converging at 1/128. It's exactly what I get. And so using this, if you can give an analytic representation of your function, if you can make a manufactured solution, you should be able to exactly know when you're going to converge for anything. I mean, right? It shouldn't be a mystery. You should be able to figure it out. So, all right, and I mean, and that should work for anything, I think. So, all right. So, here's an application model that we came up with, which is kind of fun. So these are hydrothermal vents. So we're just testing the robustness of our thing on sort of a toy problem here. So what is a hydrothermal vent? So this is a hydrothermal vent. It's an underwater vent. It's really hot. They are volcanic vents. You can find them in shallow water. Epipelagic means that light can penetrate. Hadal zones are deep. And you get these sort of metalliferous muds that surround them and come out. you get this really sediment-rich chemistry that emerges, a lot of iron sulfide. And so it's kind of an interesting and fun problem to look at just because there's a lot going on. So what we do is we take our shallow water system and we couple a chemistry to it just by adding a law of mass action here. So, and this can be done, at least these two equations can be derived directly from Navier-Stokes, multi-component Navier-Stokes. This equation is a little bit more mysterious, but I think pretty much established. And so then you have this law of mass action. You can take this initial data here, and you can couple this chemistry to it. You can look at these hydrochloride formulation reactions and serpentinization reactions, and look at how much acidity you're getting to form around this hydrothermal vent formation as it forms throughout a day. So here's an example of what it looks like when this runs. So this is just 1.5 days with really strong forcings. And you just watch it sort of grow. And it's interesting that it's stable and that you can force things at this rate, because these are fairly rapid forcings. So that was our example there. All right, so I guess, I do have time for this. Let me talk about P enrichment here real quick. So what we couple then is or what we refer to as our fast P enrichment schemes. And they come in various forms, but two that I'll present right here. One is fixed tolerance schemes. So a fixed tolerance scheme basically works in the following way. I think people have been using these basically with AMR. The idea is that you have some sort of regularity measure, some sort of energy measure, some sort of functional measure, and you want to say that if I pass some certain threshold, then I'm going to enrich. And if I am below that threshold, I might de-enrich, or I might not do anything, or if I go below something, I can de-enrich. And so it's interesting. These are interesting in that they're appealing for applications, especially. So this type 1 type that we refer to says that in areas of high energy, we resolve around those areas. So if you have a shock wave or a shock front, you can come in and you can say, okay, look, around this area of high energy or of high irregularity, high nonlinearity, whatever you want to call it, you're going to enrich or knock up the polynomial degree, okay? Which is the same, which is equivalent in some sense. I mean, it doesn't have exactly the same rate of convergence, but it's equivalent in some sense to AMR, right? So, so you're doing that around, and that's really driven by a certain sort of pragmatism that says, well, I care about things in areas of high energy where there's a lot of dynamics, right? Well, there's type 2 fixed tolerance schemes, which in some sense kind of invert that whole idea and say, wait, I don't really know if that's what I care about. Because what if all I care about is actually just convergence? What if all I care about is actually just how the order of convergence, and I want to reach a higher order of convergence? Well, if that's all you care about, then you can enrich in areas of extremely high regularity. You can enrich in areas that are very smooth. So if you have a shock front, you can enrich everywhere else in the domain. And the question is, well, can you recover? Well, the answer is actually yes. The answer is you can converge, and it's actually much easier. It's more stable too. So it's something to bear in mind. The second class that we came up with were what we call diaristic schemes. These are just similar to the above, except for now we have this sort of optimization idea in effect, where we say, look, we can afford to enrich 30% of our domain, and so we're no matter what, if we can afford it, we're going to enrich it, even if we don't necessarily care about it. We're going to sort of stay at our computational capabilities. And type 2. So, but again, you can decide sort of which way to go, where to enrich and where to de-enrich. Okay, so the way this works is, for example, you can say in areas that are non-smooth, you can approximate the regularity. So this regularity measure assumes a hierarchical basis. No, actually, it doesn't assume that, but we do use a hierarchical basis. So all we do is we take, this is the state vector. So we take a state vector, we subtract off the lower order representation of it, and we divide by the total thing. So basically what we're saying is, if we're at fourth order polynomials, this top thing is just going to be the fourth order monomial in that polynomial, or the collection of fourth order monomials in that polynomial, and then the bottom is going to be the sum of all of those things. And so you're basically weighting it. You're saying how much is the nonlinear, the higher order, the higher degree part of your thing affecting what's going on. So you just do that, and once you've decided on that, you choose a fixed tolerance based on, this is derivable, but based on whatever you want, and then you say, look, we're going to enrich around certain areas that are higher than that, de-enrich around certain areres that are lower. This is a really important thing which some people have mentioned. In fact, I think the first talk mentioned, Matthew talked about it, is how many time steps you have to wait before you can enrich. And you see the exact same type of situation arise here as you do in AMR, where you have this problem with mixing, with energy mixing, and you've got to think about it and you've got to deal with it because it dramatically affects your ability to converge. Okay. So I'll just show you a fun application that we came up with for this. So this is a eutrophication study. So eutrophication means well-nourished. So what happens is in the Mississippi River, well, what happens in rivers in general, where you have farmlands, you get a lot of nitrates and phosphates coming off from fertilizers, and they just sort of run off into the ocean. And when that happens, it just kills everything. You get these algal blooms because of the high phosphate and nitrate levels, and then the algal blooms consume all the oxygen in the water and kill everything. It's just ecological destruction. And so, and this is a problem along the Gulf Coast in general because of the types of fertilizers that have been being used in such large amounts. So the question is, that we sort of asked was, can we create sort of a toy problem to think about trying to solve this? So we take our shallow water equations here, assume a fixed bathymetry. It's not constant, but it's not time varying now. Bring in this mass action again, and then look at this equation here. So this equation takes hardened gypsum, which is just blackboard chalk, and adds it to hydrogen phosphate. So basically, what you do is so this is the Brazos River estuary. So we put a little thing right here that just emits gypsum, which is basically free, into the water. And I'm not saying that this is a good idea. This is just a test. Just puts gypsum out into the water, right? And it reacts with this hydrogen phosphate that's pouring out and tries to neutralize it and turn it into hydroxyapatite, which is just bone. And it just sort of settles into the ground, right? That's the idea. And so we wanted to say, okay, well, does that do anything? This is the bathymetry of this mesh right here. This is the ocean floor. And then we put a whirlpool mixer, so maybe just like little propellers in the water, so that you create this little whirlpool, right? A toilet bowl, right? Right here. And you ask the question, can you actually affect a change in the amount of pollution that's going out into the ocean and causing these problems? So we did this using our p-enrichment scheme. So here's an example of how that works. So this is going from order 1 to order 7. So you can see we're using a type 2 scheme here. So of course all the boundary forcings here are tidal constituents. So they're strong. And so wherever you have a strong forcing, you sort of tend to go down. And wherever you have less sort of dynamics, you tend to go up. Turns out you can do a convergence study here, and you are converging appropriately. And we say our sort of unfair suggestion, our sort of mathy suggestion, is if you can't prove that you're converging in between, then you don't have anything. Of course, you might have a great validation study, right? But that's our sort of intolerant stance. So, okay. Okay, so here's the example of the eutrophication. So here's after 29 days what happens if you don't do anything. So here's the phosphate levels. Here's phosphate levels if you just emit what was it? Yeah, the gypsum at the right here at the mouth. And here's what happens if you add the whirlpool. So you can just look at this. So the one on the left does nothing, and the one on the right is the whirlpool mixer. So you can see it's neutralizing stuff. I mean, might be creating mutant fish or something, but it's sort of working. So this, this is a fairly somewhat realistic. We've got 10 tidal constituents here. We've got, bottom friction. We're accounting for a lot of the sort of physics of the system. But of course, this is just a toy problem at this point. I mean, we've done the convergence studies. They're available. I just thought you'd be bored with that, so I didn't show you. So. Okay, so let me just say what we're. So right now we're implementing some non-hydrostatic pressure representations to recover baroclinic forcings and internal waves. We're also adding spectral wave models. So what we want to do is, particularly with the morphodynamics, is we want to try and recover a lot of the short-range morphodynamic forcings so that we can get things like sand ridges, and that we can, basically our goal is to try and run this on this hurricane model to see if we can get any of this important sort of structure that is related to these human catastrophes that occur, and have any sort of predictive ability. And now the most important part that we're adding, I think, is the sort of mortar method. So what we do is so a mortar is kind of like an adaptive thing. So you take a subdomain and you sort of glue them together in different ways where each subdomain satisfies a different I think somebody called it something else up here, but it satisfies a different equation. So if you have a coastal, if you're on like the coast, you might have a totally different sediment discharge equation that you satisfy. And it may only satisfy it for a certain amount of time, but then if you're in the deep sea, your sediment discharge equation is maybe a totally different regime. And it depends on but this is, mathematically and sort of numerically, this is going to create issues, especially at the interfaces, how you glue them together. And so that's going to be fun. So, thanks.
You never mentioned the basis you're using. What basis do you use?
We use a Dubner basis in this particular model.
So how do you distinguish between pure refinement and limiting?
Pure refinement and limiting. Well, we have P. Well, how do we distinguish? I mean, well, limiting is just taking the solution and adjusting basically for Gibbs phenomena, right?
But you're knocking out frequencies, right?
That's right. Yeah. Well, I mean, that's right. I mean, the dirty secret of DG methods. Everybody take note if you want to just hate DG methods. The dirty secret is slope limiting, right? I mean, you slope limit, you're introducing first order error, and that's just what you're doing. And there's nothing you can do. I mean, you have a discontinuous solution, and you're introducing first order error interior to cells. So that's what slope limiting does. I mean, and so we've done a fairly thorough study of slope limiting in the P enrichment regime. You guys, I think somebody here knew Dmitry Kuzmin's work, who's worked on that as well. And I think Jeff Banks has done some stuff on that as well recently. And I mean, I think if you need to slope limit in a cell, you want to de-enrich and you want to go down to linears because you got first order error anyway.
But so, I mean, it looks like when you talk about pure refinement, it looks like you're doing limiting in some sense.
Well, I mean, the goal is sort of opposite, though. I mean, for P enrichment, the goal is to try and increase the order of your solution order.
You can think of it the other way around. You can think I'm doing a seventh order simulation, except that when the simulation starts wiggling, I'll degrade the order, in which case what I'm doing is I'm using order degradation as a slope limiter. In fact, that's kind of a cool way of thinking about it.
Right, and so the reason why I'm asking this question is because
that's right.
when you go up in order,
Yeah.
I think about how do you construct a projection that you, from a lower dimensional space to a higher dimensional?
You don't. You have to start at the higher order. That's right.
Oh,
So in your equations, when you're looking at dissolved substances, you would want to avoid creating new extrema because that's what can lead to things like precipitation or
Sorry?
other. Well, if the concentration of something exceeds the physical threshold, it can start to precipitate, dissolve things. Is there any concern as you go to the higher order polynomials that you would be locally creating local extrema where you would induce precipitation, and therefore, instead of, you talked about where you want to increase the order of the polynomial, thinking about where you want to avoid increasing the order of the polynomial in order to avoid creating an extrema that would then feed back, like in a precipitation or condensation sort of.
Yeah, that's an interesting thought. I mean, in the examples that we're looking at, I think we're far below sort of precipitation thresholds, but in general, I mean, that's a really interesting thought. I suppose you can always scale that, though, right? I mean,
Or you go the other way around, and negative oxygen is, oxygen is very low.
well, if you have negative oxygen, you're non-physical, right? I mean, you can't have negative mass.
But the numerics don't know
doing
that.
that.
Well, positively preserving slope limiters do.
Right.
But yeah, sorry.
So, there's your answer. Anytime you go anywhere near an overshoot, if your indicators are right, then your P order will degrade to the point at which you're doing a low order scheme, which won't commit that sin, I guess.
And then that raises the additional complication when you're doing chemistry with interacting species. If you use different orders for different interacting species, you can get imbalances.
Oh, yeah.
Oh, well, cells are fixed order. So everybody in the cell has the same order. Yeah, that would be inconsistent, I think. Yeah. Maybe not. I haven't thought about it, but we don't do that.
If you wanted to do it at larger scale and you wanted to have like one of these balance preserving discretizations, then the relationship between the pressure and the velocity function space suddenly becomes critical, and then they have to go up and down together. And that starts to get quite complicated.
Well, I mean, the scheme is well balanced.
It's the chemistry that's potentially problematic. And that's-
The chemistry is in some sense decoupled because it's just the scalar transport in the chemistry. There's not even any chemical diffusion like fixed diffusion. It's just scalar transport. So as long as it stays out of being negative, it shouldn't affect the well balancing, I don't think. I don't know, you should tell me if I'm wrong about that, but I don't think so. Yeah.
We run into this all the time with biogeochemistry models where you have to be careful about your numerics and making sure that you don't get negative things because
Yeah.
they have a way of cascading off and
They have a way of destroying your run. I mean, yeah.
Yeah. Exactly.
You usually know when they're negative, yeah.
I'm sure John will have something to say about that tomorrow morning. Good. We're already over time, so I guess we can respectively wind up now. And look forward to seeing a lot of you at dinner tonight, and everybody hopefully first thing tomorrow morning, bright and early and bushy-tailed to do day 3. Yes.
Question with respect to dinner.
Yeah,
What
that's
is the